Hi everyone and welcome to this my video on starting to build complex numbers. Yes, this is part of the specialist maths course over here in Australia, but complex numbers are pretty universal. In fact, because maths is a constant. That joke never gets old, unlike me. Now, my name's Darren from Maths Guru. Thanks very much for joining me. Hopefully you're going to find this video useful. If you do, please subscribe to my YouTube channel and in fact give it a like. Why so few people out there actually like and watch maths videos? It is untrue. Trying to do this, I'm talking to myself pretty much, and so that little click and that like and that subscribe just lets me know you've watched and actually it is worth doing. Right, behind me are my learning objectives. What are we going to do? Understand why we need complex numbers? We don't. Finish, turn off, go home. No, I'm joking. Understand that I squared equals -1. Understand how to denote a complex number and set of complex numbers, and know the difference between real and imaginary. Now, this is pretty basic stuff, to be perfectly honest with you, and there's not really much I can recap because the chances are you've never really met this before. In fact, we've done everything we can in previous years to say, oh, there's no such things as minus square root numbers. We've sort of just ignored them. Yeah, so for example, if you ended up and we got an answer of -√3, we go, oh, that can't possibly be right. We'll just ignore it. Well, actually, we're not going to ignore it. We're actually going to deal on that today because negative square roots are actually a thing. In fact, without them, we wouldn't currently be sitting in the apartment that I'm sitting in, or the school you're sitting in, or in fact in any of the buildings, or so many other applications. All right, negative square roots, we had to do something with them. We had to turn around and go, well, okay, they are obviously a thing, right? The world is built on them, quite literally. And so we came up with a mathematical notation, convention, that allowed us to deal with negative square roots. And basically what we said was, right, well, we're going to define I squared to be -1. Now, you're going to turn around and say, what on earth does that mean? It means that then I, this imaginary number, is now going to be equal to the root of -1. So wherever I have a multiplier of -1, we can in fact now write it as I. Now, that's a very important letter. And you can't just type the letter I on a calculator. Unfortunately, it has to be very specific. Now, if I bring up my calculator, and as usual, my deepest apologies to the ClassPad users. In fact, your I is much easier to find on the ClassPad. I've only got access to my Texas at this moment in time. And so for that, I'm going to hit a calculator screen. And all the way down here where there is a pi, yes, you'll see the I in bold. Now, again, is very important with the E for the exponential. I is very important to go from here. So if I want to use this I now, I've got to use that and not this I on my keyboard. The number of people who use that and then wonder why they keep getting wrong answers is actually quite scary. Okay, so there we go. Moving on from that, what do we got? Right, so there are now things of, at the end of the day, wouldn't life be great if we just had one complex number? We don't. We have lots of complex numbers, all right? They're everywhere. And so we need to describe them in terms of a set. All right, so we've already met in previous that we got this double R, which is basically all real numbers. And you're going to now find that there is this C, or as we're going to call it, a double C. Now, that is basically to describe all complex numbers. Now, the way we define a complex number is A plus BI, okay? A plus BI, where A and B are basically in the real numbers. And you go, what? Now, for a complex number, we have two sections to it. A, which is the real component, and B, which is the imaginary component. All right, so we have a real component and an imaginary component. And again, to add even more letters to this, we use the letter Z, the small z, to stand for a complex number. So if ever you saw something like Z is equal to 3 plus 2i, we know it's a complex number. That bit there, because it doesn't have the I in it, is what we call the real. And this bit here is my imaginary. Now, again, I don't want to get too deep into the idea of imaginary friends because I've got so many of those because I haven't got any friends. I sit here all day talking to myself, really. But this terminology is going to become really important. Now, again, because we don't want to keep writing real and imaginary, it just so happens that we have something called RE of Z and IM of Z, all right? So where we see now REZ, that's just talking about the real component. That's this number. And the IMZ is basically the imaginary section, right? Happy with that? Okay, here we go. Right, so basic examples. And the great thing is your calculator has functions to be able to do this. So if we've been given the idea here that we have a complex number of the form 4 minus 5i. Find the real component of z. Well, the real component, as far as I'm concerned, is just going to be 4. Why? Because, as we said earlier, z is equal to 4 minus 5i. This number here is my real, and this minus 5 is my imaginary. Now, again, we just need to be very careful here that the mz does not include the I. And again, if ever you are unsure, bang it into your calculator and get that. Now, a word of warning with your calculator again. You'll notice in the notation there is not written as z equals 4 minus 5i. It is z becomes equal to 4 minus 5a. Now, this is actually Python notation. It's computer notation. And for your calculator means exactly the same as define. So if you said define z equals 4 minus 5i, that's exactly the same as the become equal sign. And again, let's bring my calculator up for those of you who want to know where it is. You'll notice it's here, if you can see my mouse, above this little, what is that, sort of template screen. You will notice there that there is the become equal sign, so control, and that will give you that sign. So again, sometimes use that more than I would define function. It's just easier to get to. Right, okay. What about the real? So real z, we said, was 4. mz was negative 5. Real minus m would give me 9, because 4 minus 5 would give me 9. You see, nothing particularly challenging with any of these questions at the moment. And let's continue now. Let's reverse the process, because at the end of the day, what you do forwards, you have to do backwards. So represent minus root 5 as an imaginary number. Okay, well, we can write that, he says, in highlighter as the square root of 5 times negative 1. And because of our theory, we know that can be written as root 5 times the square root of negative 1. Hold on a moment. I know what that is. So that becomes actually equal to minus, oh, try again. That becomes equal to a root of 5 times I. Now, again, the notation here is interesting because we've got to be careful that we don't actually inadvertently make that look like root 5i. So it tends to have a convention that the I tends to go at the front, just so we don't get it confused. And obviously transcription errors in maths are a huge thing. Simplify, what is this one? 2, the square root of minus 9 plus 4i. Ooh, right, well, the square root of minus 9 is equal to the square root of 9 times minus 1. That's the square root of 9 times the square root of negative 1, which gives me I times 3. So that's just 3i. Right, okay, but we got 2 lots of 3i. So that's 2 times 3i plus 4i, which gives me 6i plus 4i, or 10i. And again, what you notice here is your calculator can actually work it out for you, making sure that you do the I. And again, using the CAS is going to make your life a lot easier. Now, obviously, there's the equality. Everybody should, by this point in maths, particularly know that what that equal sign means is everything on the left-hand side must equal everything on the right-hand side. So if I have, what is that? 2a minus 3 plus 2bi is equal to 5 plus 6i. We would know that this here would have to equal my real section, and then changing my highlighter, that there would have to equal that, right? Equality, what's on the left and on the right would have to be exactly the same. So therefore we would know that 2a minus 3 would equal 5, and 2bi would equal to 6i. The i's would cancel, so b in that situation would be 3, and 2a would be 8, and a would equal to 4. And there we go. Again, fairly trivial. Are you going to get these type of questions in a VCAA exam? Probably not. Now, addition and subtraction of complex numbers, we can actually add these together. So if I had, for example, z is equal to 2 plus 3i, and let's call it z1, and z2 is equal to 3 plus 2i, you can actually add those things together. And it has a geometric meaning, believe it or not. But we're going to come back to that a little bit later on when we get to what we call Argand diagrams. So adding them, subtracting them is fairly simple. If you've got, what is this one here? So z1 plus z2 is going to be equal to 2 minus 3i plus 1 plus 4i. Now, obviously, in the same way as x's and y's, you know, you've got to add like terms together. So in this situation, you would have to add together your real sections, and you'd have to add together your imaginary sections. So what have we got here? So that would be equal to 2 plus 1 would be 3, minus 4 plus 4 gives me 1, So there we go. So Z1 plus Z2 would simply give me 3 plus I. Easy. I should cocoa. What about the next one? Z1 minus Z2. Again, have to be very careful here because we've now got 2 minus 3I minus, and in brackets 1 plus 4I. And again, the lack of those brackets means that people make mistakes with this minus and that plus there. So it's going to be 2 minus 3I minus 1 minus 4I. Again, the reals would become 1. 2 minus 1 minus 3 minus 4I would be minus 7I. And ka-ching, we get 1 minus 7I. Now, multiplying by a scalar, basically everything inside that bracket. All right, so for example here, 3Z1 means 3 lots of everything. You've got to multiply both the real and the imaginary. So we therefore get that 3Z1 minus 2Z2 would be 3 lots of Z1 would be 6 minus 9I minus, and again brackets, what's that? 2 lots of that, which would be 2 plus 8I, gives me 6 minus 9I minus 2 minus 8I. 6 minus 2 gives me 4. That would give me minus 17I, and ka-ching, we're done. Could your calculator do this for you? Yes, very, very simply. Now, Argand diagrams are basically a way of visualizing geometrically what a complex number is. And the great thing about a Argand diagram is you've really met it in terms of Cartesian planes. Except here, on the x-axis, we plot our real component. Here on the y-axis, we do our imaginary. So if we look at the idea here of 3 plus I, my real is 3, so that's 3 across. My imaginary is plus 1, 1 up, and there we go, that's my dot, right? So again, a complex number is just a point in this situation on a Cartesian, on a sort of axis shown here, all right? So minus 2 plus I, again, minus 2. We've gone 2 backwards and 1 up. This one here, 2 minus 3I, 2 across and 3 down. Now, again, visualizing what this looks like becomes really, really important. If we had to try and draw these things, what are we going to do here? This is a really, really bad idea. I should have printed off a set of axes, but there's 1, 2, 3, 4. 1, 2, 3, 4. So this is ImZ. Every time I say that, I think of Imhotep, which is the guy from The Mummy. But anyway, real Z. Put those in brackets, I think, because it makes it look a little bit easier. 1, 2, 3, 4. 1, 2, 3, and 4. Ka-ching. Right. So represent the following complex numbers as a point on the Argand diagram. So if we look at the first one here, it's 2. It's only got a real component. So I'd put a cross at 2. Oh my goodness, they said this was complicated. Minus 3I, well, that's my imaginary. So minus 3I is going to give me down here. 2 minus I suppose we should actually label these as well. So that's minus 3I. What do we got here? 2 minus I. So it's got both a real and an imaginary component. So 2 across and 1 down is going to give me 2 minus I. That's going to be there. Minus 2 plus 3I. Well, that seems a bit silly to me. So minus 2 minus 3I is going to be here. So there's minus 2 minus 3I. And what's the last one? Minus 1 plus 2I. Minus 1 plus 2I is going to be here. So there's minus 1 plus 2I. Okay, again, not complicated. Not at the moment, but trust me, it does. Now, vectors and complex numbers seem to share various similarities, and we can think of adding and subtracting complex numbers in much the same way as we do with vectors. All right, also can extend to multiplication with scalar too. But let's look at this example here. So what have I got? I've got 2 vectors. I've got Z1, 2, not vectors, 2 complex numbers, 2 plus I, and Z2, which is minus 1 plus 3I. Now represent the complex numbers Z1, Z2, Z1 plus Z2, and Z1 minus Z2 on the Argand diagram. Right, well, if I do Z1, it's 2 plus I. So there is my Z1, and my Z2 is minus 1 plus 3I. So there is my Z2. They are my 2 points. Now, if we were to do the mathematics between Z1 plus Z2, Z1 plus Z2, what would we get? We'd get 2 minus 1, which would be 1. And we get 1 plus 3, which would be 4 plus 4i. So 1 across and 4 up. So let me see. Have I got that? 1 across and 4 up. There we go. Now, basically, what we seem to have done is if we've actually got this point here as Z1, and my Z2 there is effectively 1 back and 3 up, then what I seem to have done is gone 1 back and 3 up to basically get to my z1 plus z2. If I was going to do z1 minus 2, what do you reckon you're going to do? z1 minus z2? Well, we're basically going to reverse the operation. So z1 minus z2, rather than going, what is it? Where's my pen? Rather than going 1 across, 1 back and 3 up, we would go 1 to the right and 3 down. So 1 to the right and 3 down, and there we go, z1 minus z2. Now, trying to keep that in your mind when you're doing this type of stuff can help later on with the more complicated questions. Now, multiplication of complex numbers is huge. It comes up over and over again. The next video particularly is going to build on that. But again, the techniques behind these are pretty much FOIL, all right? You've done FOIL but inside out and backwards. So if we look at the first one, there's 2 plus 3i and 1 minus 5a. You have to be careful of the trick here. So I'm going to do first times first, first times second, second times first, second times second, or what is it? FOIL first, outside, outside, inside, last, or whatever it is. Stupid expression, but anyway. So 2 times 1 gives me 2. 2 times minus 5i gives me minus 10i. 3i times 1 gives me plus 3i. Now, here we've got to be careful. 3 times 5 gives me minus 15, and I times I gives me I squared. Now, again, if you go back to the start of this video, remember, we defined that I squared was equal to minus 1. Aha! So basically, that gives me 2 minus 10i plus 3i minus 15 times minus 1. So 2 minus 10i plus 3i plus 15, and simplifying that is going to give me 17 minus 7i. All right, now again, look at the convention. We always write the real bit first and then the imaginary bit. All right, so what about the next one? Well, you've got 3i times 5 minus 2i. Again, that's going to be 15i minus, he says 2. 3 times 2 is 6. I squared. I know that I squared is minus 1. So it becomes 15i plus 6, or 6 plus 15i. Again, make sure that your notation is the right way around. I cubed. Well, again, we're going to build on this a little bit more later on. So that's basically the same as I squared times I. I squared is minus 1 times I. So it simply become minus I. Now, a lot of these tips and tricks and these things we use a little bit later on. Now, I suppose one of the most important questions, and again, geometrically, this is really, really important, is what does it mean to multiply by I? Right? What does it mean to take something and multiply by I? So I thought I would show you. Let's assume I've got a complex number at the point 3 plus 2i. So there it is, 3 plus 2i. So if I've got 3 plus 2i, and I multiply that by I, I'm going to get 3i plus 2i squared. I squared is minus 1, so you get minus 2 plus 3i. Now, when we plot minus 2 plus 3i, what do I notice? Well, there's my z2. Now, if I multiply that again by I, I'm going to end up with, actually, this point here. And then again, I get this point here. And then again, I get back to the beginning. Now, what you would notice was, if I was to actually connect these, hopefully using straight lines, there we go, we're going to do that, and we're going to do that. If I was to measure that angle there, it actually is a right angle, all right? And that's actually true of all of those. So what's happening is, when you multiply by I, you're actually rotating, or you're, rotating anti-clockwise by 90 degrees. And again, that type of thing can come in really, really, really handy later on with the visualization. Now, powers of I, let's get into this because, again, it's really, really funky. Right. I to the power of 0 is 1. Anything to the power of 0 is 1. I to the power of 1, I. I squared, minus 1. I cubed, we decided a moment ago, was minus I. And I to the power of 4, 1. I to the power of 5, I to the power of 6, minus 1, I to the power of 7, I. So it seems to oscillate. If we continue doing this, it would oscillate between 1, I, minus 1, minus I. 1, I, minus 1, and minus I, all right? Now, in general, we can therefore say that because this seems to have 0 to 4, 1 to 5, 2 to 6, 3 to 7, it goes up using the 4 times table. So we can generalize that I to some sort of power of 4, or multiple of 4, I should say, sorry, would always be 1. I to a multiple of 4 plus 1 would be I to a multiple of 4 plus 2, minus 1. And some sort of multiple of 4 plus 3 is minus I. This type of stuff should absolutely go into your summary book. Now, the reason I've put this in, a VCAA question, and what I'm normally going to do now is put a sort of whole section of VCAA questions in each chapter, is to say, well, this is how they can try and trick you, okay? This is amazing. All right, now I really love this question. Can I bang it to my calculator? No, because actually what this is saying is, if you were to take I to the 1 factorial plus I to the 2 factorial plus I to the 3 factorial plus all the way up to I to the 100 factorial, what's it going to be equal to? And there's no way you guys are probably going to be able to put that into your calculator, certainly in the time that they've given you in the exam. So let's think, what is 1 factorial? It's 1. What is 2 factorial? It's 2 times 1. 3 factorial? 3 times 2 times 1. 4 factorial? 4 times 3 times 2 times 1. Okay, so let's work out what this means. So if we've now got I to the power of 1 factorial is I to the power of 1, plus I to the power of 2, plus I to the power of 6, plus I to the power of 24, and that is 4, 12, 24. And so it goes on to, well, does it matter what it goes on to? Because we now know I to the power of 1 is I squared is minus 1, I to the power of 6. What is I to the power of 6 going to be? It's going to be I squared times I squared times I squared. That's going to give me minus 1 times minus 1 times minus 1, which gives me minus 1. Now, what about I to the 24? Oh, well, hold on a moment. That's a multiple of 4. And any multiple of 4 gives me 1. All right, okay. So I'm going to add 1 on there. And then what do I got? Well, I to the power of 5 factorial. What's 5 factorial? Well, actually, it doesn't really matter what 5 factorial is, because number-wise, we know that that's 5 times 4 times 3 times 2 times 1. But ultimately, we got a 4 in there. So all of these are going to be some sort of multiple of 4. And we know that multiples of 4 are actually always going to be plus 1, plus 1, plus 1, and all the way up. So we've got I minus 2 plus, well, how many numbers are there? Well, it's going between 1 and 100. So we've already got 1, 2, 3 of them are not included in 100. So that's 97 of them are going to be equal to that. So in which case we're going to get I plus 95, which tells me, therefore, that C is going to be my correct answer. Now, in the VCAA exam, that this was in 2019, only 44% of the state got that question correct. And again, it came more down to the idea of factorials and logic, and knowing that from 5 factorial on, they're all going to be factors of 4, or multiples of 4, and so it moves on. Now, this turned out to be a really, really interesting question. And again, it looked at the idea of your algebra and your complex numbers and your powers of I and all that type of stuff together. So let's see where we go with this. We've been told that x plus iy to the power of 14 is a plus ib. Okay, where x, y, a, and b are all real. Y minus ix to the power of 14 for all values of x and y is going to be equal to. Right, okay, so let's see where we go with this one. Y minus ix to the power of 14. A lot of people said, well, just take out minus 1. Sadly, you can't. Why? Because the I is basically stuck to the x there, or negative I is stuck to the x there, and yet it is stuck to the y there. So it was a little bit more complicated than that. Now, what I'm going to do is say, well, I want to take out, let's take out minus I out of this set of brackets. I'm not going to worry about the power for the moment, and that's going to give me x inside my brackets. Cool, that works. So I've got my x, I've got my x. What am I going to try and do now? Well, I've got to have a y here. All of that's going to be to the power of 14. So minus I times what is going to give me plus 1. So I know that minus I times minus I is going to give me, what is that going to give me? Minus I times minus I is going to give me plus I squared, which is minus 1. Do I want minus 1? I don't. I want plus 1. So let's take that as just I then. All right? So minus I times I squared is Yep. So in which case I want that as plus IY. Now, a lot of you are probably screaming at this going, yes, well, that was really obvious. Yes, I know that, but I'm trying to show my thought processes to people who are doing specialist maths who aren't necessarily as quick off the mark as many of you already are. So please bear with me there. Right. Well, hold on a moment. Why is that important to me? Well, I've got another rule useful from year 9 that AB to the power of n is a to the power of n, b to the power of n. Oh, okay then. So what that means is I can now write that as minus I to the power of 14 times by x plus IY to the power of 14. Oh, well, why is that useful to me? Well, they already told me that x plus IY to the power of 14 is a plus IB. So that's a plus IB. What is minus I to the power of 14? Well, that's going to be basically 4n plus 2. So if I go back here to 4n plus 2, yes, 4n plus 2 is negative 1. So what that means is that actually is minus 1, which therefore gives me minus a minus IB. Can we find an answer that's minus a minus IB? IB, yep. And there we go. A is our correct answer. And believe it or not, that's the end of this video. Hopefully it has been useful. Do we understand why we need complex numbers? Yes, otherwise we wouldn't have buildings or engineering. Understand that I squared equals minus 1. Okay, that's useful to know because it's going to help us now with our root signs. Understand how to denote a complex number and sets of complex numbers? Yes, so the complex, all our complex numbers are double C's. Understand how to denote it? Yep, A plus IB is going to be useful. Know what real and imaginary numbers are? We do, and so I think we're done. Thank you very much for watching. If you can subscribe to my YouTube channel and like this video, I'd be deeply, deeply grateful. I record this for you guys, hoping to help you get better at maths. Now, the other thing you got to do is practice, practice, and practice. Find out where you're going to trip up. That is massively important. I'm going to record another video. Hopefully, I'll see you in that one. If not, take care and stay safe. Bye-bye.